Good afternoon to all of you. In continuation to your last lecture, we have seen the posterior probability, determination of posterior probability. Here, determination of posterior probability, that is probability of mk given q is equal to probability of mk into probability density function, conditional probability density function for q given mk divided by probability density function for q. Here we have to find out the posterior probability. Posterior probability is q is already received at receiver, and we have to define the probability of transmitting the symbol mk. That is given as probability of mk. This is a prior probability. Transmitter first of all decide it is going to send the how many bits, how many symbols, and what is the probability, corresponding probability. Suppose we are sending 0 and 1. When they are equiprobable, then we can say that the probability is 0.5, 0.5. When we are sending the m symbols, when they are equiprobable, then every symbol has the probability 1 by m. That is multiplied with conditional probability density function, that is q given mk, and here probability density function for q. In this case, for particularly when we are interested with any symbol I, so we can see that probability of mi given q is equal to probability of mi conditional probability density function q given mi divided by probability density function for q. We will get a maximum value. This will give the maximum value for I is equal to k. For I is equal to k. That means your transmitter sends the kth symbol and receiver receives the kth symbol. This is called as a posterior probability. Here, this quantity is common for all m. This probability density function for q is common for all m, so we have to neglect this one. Write down, this is a common to all decision functions, therefore we have to ignore that quantity. So here finally we will get a probability density function, that is probability of mi into probability density function, conditional probability density function q given mi. Here I is ranging from 1 to up to capital M. Now here probability of mi, this is the prior probability. Transmitter has to decide this probability, then probability density function of q where mi is already transmitted. Here we will get a maximum value for this one for I is equal to k. Is it clear to all of you? In this way we have to define the posterior probability. Posterior probability, that is the probability of mk or mi given q is already received at a receiver. Now we have to make a, write down computation of decision function. Write down computation of decision function. Here the probability of mi is a posterior probability which is decided by transmitter. Now I am standing at your receiver. I have to make a decision about which symbol is received by your receiver, out of which probability of mi, this is our prior probability which is decided by your transmitter. Here either it is equiprobable or non-equiprobable. So we have to define or compute the probability density function, which is a conditional. We have to find out the probability density function for q vector, provided this mi symbol must be transmitted from your transmitter. So here we are having q is given as si plus n. What is this Q? X of t. X of t is equal to Si of t plus n of t, out of which we have to devise this noise, which is a infinite bandwidth, Ni of t. This is a part of noise which can be represented on n-dimensional signal space, and n naught of t, this is a part of noise which cannot be represented on n-dimensional signal space. So here Q is nothing but Si of t plus Ni of t, and n naught of t is already filtered out because this noise is perpendicular to all the n-dimensional signal space. So their dot product or their projection on n-dimensional signal space is 0. So here Q is equal to Si plus n. Here we can see that n is a random variable. Is it? N is random variable or random point. This Si, is it a constant value? Yes or no? Si is a constant value. N is a random point. So finally this Q, what is this Q? Is it a constant or random variable? Random variable. So from this one we have to find out this n. N is equal to Si minus, this is Q minus Si. Q minus Si. So here we can see that Si is your constant. Write down. Si is equal to constant. Si is equal to constant. N is a random point. Therefore Q is a random point. Therefore Q is a random point with distribution which is equal to distribution of n, which is equal to distribution of n, but center at in bracket or with mean value bracket close the points Si. The points Si. See here, Q is a random point, N is random point. Whatever the probability associated with your N or probability distribution associated with N is equal to probability distribution of Q. Is it clear? Both are having the same probability distribution. But when S introduced, then what happens? Whatever the probability distribution function for N, it is get shifted with Si. This is the same case. When we are having the X is a random variable which is centered at 0 mean. When we have to introduce its mean value mu, then this random distribution is get shifted with mu value. This is the case. Suppose we are having a probability density function for X random variable which is centered at 0. Same random variable when we introduce here we can see that this density function gets shifted with some constant value, that is mu x. That is mu x. Here we can see that this Q gives the distribution function which is equal to n but which is get shifted with Si constant. So here we can see that Si is nothing but a mean value or center value for this one. So here, therefore probability of Q, write down probability of Q given mi, this is the conditional probability. We are finding the probability of Q, but mi should be transmitted prior. So probability of Q given mi is equal to probability of n that is equal to q minus si, that is equal to q minus si. Here we can say that probability distribution function for q, probability density function for q given mi, that is equal to probability density function for noise for q minus si. Is it clear? Yes or no? So here this will be, now we are finding the probability density function for this noise. This is given as 1 by pi with this italic n. This italic n stands for PSD of your noise, that is italic n divided by 2 raised to capital N by 2 into e raised to minus q si square divided by italic n divided by capital N. Is it clear? This is the probability density for noise given as 1 by pi italic capital N, that is the power spectral density of your noise for white noise, raised to capital N by 2 into e raised to minus q minus si square divided by eta. As these values are equal, here this is your decision function, probability of mi into probability density function of q given mi, both are equal. We have to put this quantity here. Just put this quantity here, we will get this decision function becomes probability of mi divided by pi into italic capital N raised to capital N by 2 into e raised to minus q minus si square divided by italic n. Is it clear? Our job is we have to find out the decision function. This will give us probability of mi into conditional probability distribution. This conditional probability distribution is equal to probability density function for noise where n is equal to q minus si. That distribution is given as 1 by pi into italic capital N PSD of noise raised to n by 2 into e raised to minus q minus si square divided by italic n. Now we have to put this quantity here. So we will get probability of mi divided by pi into italic capital N raised to n by 2 into e raised to minus q minus si raised to square. This is normalized factor. It will use the distance divided by italic capital N, which is greater than or equal to 0. So write down, as this quantity is non-negative, as this quantity is non-negative, it is always greater than or equal to 0. We have to apply the logarithm. We have to apply the logarithm. As this quantity is non-zero, we have to take the logarithm for this function. And here, this quantity is here, this pi into italic capital N raised to pi by n, it is common for all m. This quantity is common for all m's. So we have to ignore this one. Write down here. This quantity is common for all I. Therefore, we have to ignore this quantity. We have to ignore this quantity. Now we have to take, so here we will get natural log of probability of mi minus 1 by italic n q minus si square. Now this is called as decision function. This is called as decision function. Is it clear to all of you? Can I repeat this point? See here, our aim is we have to design such a detector which is called as optimum detector by using signal space analysis. The transmitter is going to transmit the symbols, that is mk. After modulation we will get sk signals, sk of t. Now these signals are transmitted over the channel, then channel introduces the noise n of t. Input to the receiver is x of t, that is given as si of t plus n of t. Now our job is we have to represent this input x of t in geometric representation. So as per the Gram-Schmidt procedure, we can represent this sk of t on n-dimensional signal space diagram, where n is less than or equal to capital M, n gives the number of basis function. Similarly, we are having a noise which is the input to your receiver. Our job is we have to represent this noise on n-dimensional signal space. So out of which we have to split this noise which is having the infinite bandwidth, some part which can be represented on this n-dimensional space and some part which cannot be represented on this one. So the part which can be represented here, we can say that ni of t, and remaining part, that is n naught of t, which is the perpendicular to this n-dimensional. So dot product or projection of this part on n dimension is almost 0. That's why we have to filter out this part without affecting the message signal. So finally we have to plot the sk of t, which is on n dimensional by using n basis function. Similarly, we have to plot your ni of t, noise part, on this one. And we have to take a decision. You are transmitted the m symbols, m1, m2, m3, or sk, s1, s2, s3 up to sm, out of which your receiver receives which signal, which symbol is received by your receiver. We have to make a decision over this one. Assume that your transmitter transmitted two symbols, that is 0 and 1. They are equiprobable. They are equiprobable. That means their probability is 0.5, 0.5. Then we have to plot these two signals on your n-dimensional signal space analysis. Here, for this signal, suppose your transmitter transmitted two symbols, that is S1 and S2. This is from your transmitter side. Then we have to connect these 2 points. As they are equiprobable, we have to divide equally. Distance from this boundary to S1, boundary to S2, they are same. That means we are having region R1 and region R2. And at receiver, we are going to receive this Q. We have to plot this Q on this Q1 and Q2 on this two basis function diagram. Suppose Q1 is placed here. This Q is placed here. This is the point. Now we have to make a decision about S1, whether this S1 is transmitted or S2 is transmitted. We have to find out the distance between this S1 and Q. Which one is the minimum distance? It is more closer to S1 or it is present in the region of S1. So we have to confirm that. S1 is transmitted. When this point is present here, we can see that it is present in your region of 2. So S2 is transmitted. When we compare this distance, or we have to compare this distance, which one is the smaller? From S1. So we have to make a decision, that is S1 is transmitted. Same rule, same decision is given by this decision function. Here, natural log of probability of Mi minus 1 by italic capital N, that is the power spectral density of your noise, into mod of Q minus Si. This is a distance. This will be distance. This will be distance, square value. Whatever the value is minimum, we can say that symbol is transmitted. So please confirm with this decision rule. Is it clear? Yes or no? Now here, see here, this will be the decision. Now this Q minus Si square is nothing but Q minus Si dot product with Q minus Si. This will be gives dot product. Q minus Si square, the magnitude value gives the distance, is nothing but a dot product of this distance, Q minus Si dot with Q minus Si. This will be given as mod of Q square plus Si square minus 2Q into Si. Minus 2Q into Si, out of which multiplying throughout by capital italic N by 2, just divide this equation, multiply throughout by capital italic N divided by 2, we will get by 2 natural log of probability of Mi minus 1 by 2, here mod of Q square plus Si square minus 2Q into Si. This point is clear. This is the prior probability. When we are sending the 2 bits with equiprobable, this probability is 0.5, 0.5. So natural log of probability of 0.5. Natural log of 0.5. This is a constant quantity. So here this Q minus Si with dot product of Q minus Si, it can be represented as mod of Q square plus Si square minus 2Q into Si. Here by multiplying with capital italic capital N by 2, natural log of probability of Mi minus 1 by 2 Q square plus Si square minus 2Q into Si. Here this quantity is nothing but, is it a energy associated with your input symbol? Yes or no? This can be represented as EI. This is a EI quantity. So in this equation we have to AI is equal to 1 by 2 here. This quantity is constant minus 1 by 2, this EI energy which is associated with your input symbol. We are using the rectangular pulse or sync pulse, whatever the energy associated with your input symbol is constant. So we have to collect these quantities and represent this AI is equal to 1 by 2 and natural log of probability of Mi minus EI, that is equal to constant. This is a quantity. So here this equation becomes AI plus Q into Si minus 1 by 2 q square. Now this equation becomes, just we are representing this equation by collecting the terms which are constant, that is ai, which represent 1 by 2 in bracket n into natural log of probability of mi minus ei. This is the constant quantity. Just this equation becomes ai plus q into si minus 1 by 2 q square, out of which this quantity 1 by 2 mod of q square, this is a common for all I. Write down, common to all m or I decision function. So we have to ignore that quantity. As this 1 by 2 into mod of q square is common for all m, so we have to ignore this quantity. So decision function becomes bi is equal to ai plus q into si. This is your final decision, that is bi is equal to ai plus q into si. This will be given as your 1 by 2 see here, just we have to elaborate this decision rule. Finally decision rule is given by bi is equal to ai plus q into si. I am standing at receiver point. I have received the sum vector, that is q, which is a combination of si plus ni. So our job is we have to plot this q vector on n-dimensional signal space diagram. Depending on this one, and prior we have to plot the points from your message symbols which are transmitted from your transmitter, that is S1, S2 up to Sm on same signal space diagram. Finally, we have to find out the minimum distance between this q minus si. They will decide which point is actually, which symbol is actually transmitted from your transmitter. Now I am making this decision at receiver side. I do not know about the transmitter, which symbol is transmitted, but we require some point, that is from this one we can see that this is italic capital N, this is the power spectral density for your white noise, natural log of probability of mi. From your transmitter we must know what is the probability of all symbols which are transmitted from your transmitter. When they are equiprobable, then this probability is given by 1 by m. When they are not equiprobable, then we are assigning the different probabilities with different symbols. Then minus ei, the energy associated with your input symbol, whether it is a rectangular signal or sinc function, the energy associated with this symbol, I am not interested with whatever the shape of symbol, but what is the energy associated with this one, plus q into si, this dot product. By depending on this quantity, I have to fix the decision. I have to fix the decision which should be correct decision, that is probability of C. What is correct decision? Correct decision is nothing but m cap is equal to mk. M cap is equal to mk. So we are having, transmitter sends the m symbols, that is S1, S2 up to Sm. On the signal space diagram, we are having corresponding regions, that is R1, R2 up to Rm. Now our job is we have to find out this q vector which is a received vector, is going to place on which region, or it is more close to which region. Depending on this one, we have to take a decision that which symbol is transmitted from your transmitter. It is clear? Yes or no? Decision regions and error probability. Decision regions and error probability. The signal space is divided into capital M, non-overlapping or disjoint decision regions. Disjoint decision regions R1, capital R1, R2, R3 up to Rm. Corresponding to capital M, M1, M2, M3 up to M capital M messages. If Q falls in the region RK, if Q falls in the region RK, then decision is that MK was transmitted. Then decision is that MK was transmitted. See here, for corresponding M symbols, we are having the regions R1, R2 up to Rm. We have to receive this Q vector. Your receiver receives this Q vector. Your Q vector is going to place near to any region, whether it is R1 or R2. Just assume that this Q vector is situated in your region R3. Then we can say that when Q is lie in R3 region, then we can say that our decision is M3 symbol is transmitted from your transmitter. So the decision function for correct decision, write down the decision function for correct decision is M cap is equal to Mk. This given as natural log of probability of Mi minus 1 by italic capital N into Q minus Si square. So this will give italic capital N natural log of probability of Mi minus Q minus Si square. This will be maximum for I is equal to K. This will be maximum for I is equal to K. This Q minus Si gives the distance between point Q and Si. Write down this Q minus Si gives the distance between point Q and Si. Now here we are having the two cases. Case 1, equiprobable messages. First case is equiprobable messages and second case is non-equiprobable messages. First of all, we have to see case 1, equiprobable messages. That means whatever the symbols transmitted from your transmitter, they are equiprobable. So probability of Mi, that is a prior probability, is equal to 1 by M for all I. Write down probability of Mi for first case is equal to 1 by M for all I. Is it clear? So here in this function, this is a decision function. Italic capital N, power spectral density of noise, white noise, into natural log of probability of Mi. Here this quantity is fixed, 1 by M. for all I. Can I ignore this one? As this quantity is common for all the I functions? Yes, ignore this one. So finally we are having this quantity, that is minus q minus si square. Yes, for this first case, which is the equiprobable, your decision function becomes minus q into si square. This will give you the distance between point q and si. So for your decision, which is a correct decision, that is m cap is equal to mk. This value, that is minus q minus si square, it should be larger. Yes or no? To get a correct decision, that is m cap is equal to mk, the probability of C, it should be larger. Here we can see that to get a correct decision, this decision rule, it should give a maximum value. For equiprobable case, this quantity is constant, it is common for all I or m, we have to ignore this quantity. So finally we will get minus q minus mod of q minus si square. This quantity should be larger. But in numerical case, we can see that this quantity should be smaller because this minus sign is present. So next situation is here, that is this distance q minus si square is minimum for I is equal to k. Is it clear? This point is clear? To get the correct decision, from this decision rule we can see that this minus q minus si maximum, it is equal that q minus si square, it should be minimum. Is it clear? Due to this minus sign, we are going to say that it is larger. When we are removing this minus sign, this becomes smaller. And this is the distance between q and si. Q and si. So we have to select 2 points, S1 and S2, which can be represented, these 2 signals can be represented by 2 basis function phi1 and phi2. Is it clear? We are having for example, we have to consider, we are having the 2 signals which are transmitted from your transmitter. They are S1 and S2, and we have to plot these 2 signals on signal space 2 dimensions. Here 2 basis function phi1 and phi2. So this is your S1, this one is your S2. Here we have to connect these 2 points. We have to connect these 2 points. Then as they are equiprobable, find out the middle, and we have to draw the line which will divide, which is perpendicular and divide these 2 regions. Here. So we will get region R1 and region R2. Upper one is region R1, lower one is region R2. Is it clear? For representation of these signals, we are using 2 basis functions. So n is equal to 2 and m is equal to 2. Now see here, receiver receives the signal, that is q, vector q, which is having si plus noise is present. Due to this noise, suppose this is the point q. Can you make the decision which symbol is transmitted from your transmitter? S1. Why this one? It is more closer, or we can say that the distance between these 2 points is minimum. This is the distance. We have to place a point bar that gives q minus si. Whatever the minus or plus, it will only give the distance. So here this distance is minimum, so our decision is correct. Here for this case we can see that M1 is transmitted, otherwise M2 is transmitted. This is the case for equiprobable. As they are equiprobable, we can divide this line equally. We can divide this line equally. Now for the case, write down second case. Is there any question regarding this one? Write down second point, that is for non-equiprobable. Non-equiprobable, here for same case we are having 2 points which can be represented by n is equal to 2 basis function. These 2 points are given S1 and this one is S2. Connect these 2 points. Now here they are not equiprobable, so divide them. So we will get this distance. This is mu, and from this point this is d minus mu, and here this point is present q. The boundary which will divide the region for S1 is R1 and R2. The distance is not common. They are divided with mu and remaining part is d minus mu. The distance between these 2 points is given by small d. So here write down the decision is M1. If the decision is M1, decision is M1, so for this decision, natural log probability of Mi minus 1 by italic capital N q minus Si square. This equation becomes q minus S1 square minus italic N natural log of probability of M1 is less than q minus S2 square minus italic natural log probability of M2. Here this decision rule for M1 symbol is transmitted. Here we will get q minus S1 square, distance between point Q and S1 square minus probability density function PDF for noise into natural log of probability of M1. Whatever the probability of M1, here we have to consider this probability of M1 is 0.7 and for this one 0.3. As they are not equiprobable, probability associated with your first symbol is 0.7, which is larger than your second one. So here we will get this equation q minus Si 1 square minus PDF for noise into natural log of probability of M1. This is a decision rule, decision function for decision of M1. It should be less than the decision for second symbol, that is q minus S2, distance between this point and this S2. It should be minus PDF into natural log of probability of M2. It should be larger. So this distance is larger. So otherwise, when this condition is true, we will get M1 is transmitted. The decision is M1, otherwise M2. Write down, otherwise M2. So here we have to take this q minus S1 as a d1 is equal to q minus s1, and this d2 is equal to q minus s2. In this equation we have to place q minus s1 is equal to d1 and q minus s2 is equal to d2. So this function becomes d1 square minus d2 square is less than PDF of noise natural log of probability of m1 divided by probability of m2. d1 square minus d2 square, here distance between q and s1 is d1 and distance between q and s2 is d2. So d1 square minus d2 square in this equation is less than PDF for noise into natural log of probability of m1 divided by probability of m2. So here this quantity is fixed, probability density function for noise is fixed, natural log 0.7 divided by 0.3, it is again fixed. So we can see that this quantity is constant. Is it a constant? Yes or no? So this is equal to C. This is called as a constant. Now regarding this one, when d1 square minus d2 square is less than this C, where in the three situations d1 square minus this d2 square is greater than C and d1 square minus d2 square is equal to C. In first case we can say that your symbol m1 is transmitted. In second case m2 is transmitted, and in third case point is lie on, q is lie on boundary, q is lie on this boundary, q is lie on boundary. Q is lie on boundary. So here we have to find out this mu, d and c. This point is s1, s2, this is your q. This one is mu, d minus mu, this is alpha, d1, d2. Same diagram. Here this is your point q, d1, d2, mu, d minus mu, and distance this is alpha. Now depending on this one, write down from this figure, d1 square is equal to alpha square plus mu square, d2 square is equal to alpha square plus d minus mu square. So here this quantity d1 square minus d2 square is equal to 2d into mu minus d square is equal to c, which is a constant. So here we will get this value mu is equal to c plus d square divided by 2d. Here c is a constant, we have to find out this c constant, then we will get a d, distance between this s1 and s2, and we have to find out this mu is equal to c plus d square divided by 2d. Then for m messages, this is true for only two messages. For m messages where m1, m2 up to m capital M gives the region R1, capital R1, R2 up to Rm, capital M. So probability of C Mi is transmitted, that is equal to probability of Q lies in the region Ri. So probability of correct decision when Mi is transmitted, that is equal to probability of Q lies in Ri region. Here we can see that M1 is transmitted. What is the probability of correct decision when M1 is transmitted? That is equal to probability of Q, this Q lies in R1 region. When it is going to lie in R2 region, then it will give the error. So write down probability of error. Probability of error, that is equal to 1 minus probability of C. 1 minus probability of C. In this case, we have sent 3 symbols. They will corresponding regions. Here S1 and S2, they are divided with this line. S1 and S3 is divided with this line, this one, and S2 and S3, they are divided with this line. So we will get region R1, then this region is R2 and R3. When Q vector lies here, we can see that second symbol is transmitted. Second symbol is transmitted. This is the true for M symbols. The transmitter transmitted M symbols. We are going to place these M symbols on n dimensional n basis function. So we will get the corresponding regions R1, R2, R3. Now our job is we have to plot the Q, which is a combination of Si plus noise part, which can be represented on n dimensional signal space, that is n basis function, where Q is going to lie in which region. That means that particular symbol is transmitted from your transmitter. This is called as optimum detector. For this optimum detector, we require some decision rule. This is given as natural log of probability of Mi, italic, or finally here Q minus Si. In this way, we have finished this chapter.